Hello everyone and welcome again to another session with the Cyber Professor. Today we will continue our discussion regarding operating systems, and as you may remember, we discussed an introduction to operating systems in our first session. Then we moved to the first few concepts regarding processor management and synchronization of processes, and then we stop right there to give you some time to think about the definitions that we provided to you during the first two sessions. And now we are ready to conclude the discussion on processor management by touching upon the way we can alleviate some of the issues that come with process synchronization, some of the techniques that are used to prevent some of the issues that are related to process synchronization. And then we are going to talk a little bit about the concurrent processes and the parallel processes that are typically present in a system that has multiple processing units or CPUs. With that, we are going to be finished with the section of our course in operating systems that is specifically focused on process management. So let me switch some screens and get ready for our presentation right now. I'm going to share my view of the PowerPoint presentation. Okay, so we should be ready to go now. And as you may remember, we mentioned that we are going to talk about the course map every single time that we get an opportunity, because it is important for us to make sure that we remain on track on our plan on how we are going to address the different portions of operating systems concepts. So with that said, let's move to the course map. All right. So in our first session, we touch upon Introduction to Operating Systems. This is number 1 in the course map display that I am showing to you. And then we move to Processor Management as our second topic of discussion for operating systems. And as I mentioned during the first session, we covered the process management and synchronization of processes. And today we are going to conclude number 2 in our course map with the discussion on some of the techniques that can be used to alleviate issues that come into play when you are synchronizing processes within any computer system. That will be the first item that we are going to discuss, and then we are going to move to the concurrent processes, the parallel processes, and explain a little bit about the differences between the two. So those are terms and concepts that many times come at you and you believe they mean the same thing. However, there are some differences between the two concepts that I am mentioning to you: concurrent processes and parallel processes. So with that said, let us do a quick review of what we have been discussing in the previous session. Chapter 4 was concentrated on processor manager. What is a program? We discussed what is a program. We talked about a process, the program being the passive component, the code that is written by the developers, and the process being kind of the active component, the execution of some of the tasks that are part of the code that came with the program. So process is the active component whenever you have those code and the instructions loaded into computer memory for execution. So that's what a process is. And then we came into the concept of thread And thread being a subcomponent of a process, and we said that threads can be found in processes, and there may be more than one thread per process. And processes are typically depicted in the task manager view of your computer. You can see a huge list of processes that may be running at any point in time on your computer system, and you can view how they are listed under Task Manager. And by the way, let me do a quick view of Task Manager for you so you can take another look before we continue this discussion. It's very important for you to remember that concept, because that is highlighting the way that your computer system and the operating system that is running on your computer system is so critical to make sure that everything is working well for you. So if you take a look at the Performance tab under Task Manager, by the way, you can access Task Manager by just pressing Ctrl-Alt-Delete on your keyboard if you're running a Windows computer, and then select Task Manager after pressing Ctrl-Alt-Delete on your keyboard. So with this view of Task Manager, if you go to the Performance tab, you will see that there are 353 processes running on my computer, and that ties into our discussion. Remember, processes are the ones that we talk about during our first session, and this is telling us there are 353 processes running on my computer and 5345, so that is 5,342 now threads running under those 353 processes. So this is proving to you that the concept comes to life when we are viewing how the processes and the threads are part of the operations of my computer system. So again, processes being the active component of a program, the code put into memory on a computer system ready for execution, and the fact that there are one or more threads in any given process that is running on my computer. So that is why you have a high number of threads listed here. If you want to take a look at the processes that are running on my computer, I just switch to the Process tab and you will see a huge list of processes here. So let me close Task Manager. So that is the main important topic that we discussed during our first session. Then we move to the concept of PCBs, or process control blocks, as another component of our discussion related to processor management. And then we talk about process and context switches and how the CPU is able to handle multiple tasks, multiple jobs by doing context switch and process switch, and the difference between the two. Then we talk about process and CPU scheduling, preemptive and non-preemptive scheduling, and finally we listed some of the scheduling criteria and algorithms that are part of our chapter. So these are the slides that we covered in our previous session. These are the scheduling algorithms that I mentioned, with a clear definition whether or not they are preemptive or non-preemptive. And then we moved to chapter 5, and we said we were going to cover the first two sections of chapter 5, and we talk about system deadlock and live lock and how they can occur. We also talk about some of the differences between the two, deadlock and live lock, and then how processes can become deadlock. That's when we decided to stop and move to the end of the session and get ready for the second session. So this is the last slide that we covered in our previous presentation with the deadlock, and the fact that something important that I want to highlight so we can connect the dots with what we are going to discuss today is the deadlocks. The deadlocks, we mentioned that there are 4 conditions that need to take place for a deadlock to occur, and those 4 conditions, we listed them here, being mutual exclusion, hold and wait, no preemption, and circular wait. Those are the 4 conditions that must be present in order for a deadlock to occur. Just as a refresher, a deadlock is a problem occurring when the resources needed by some jobs to finish execution are held by other jobs, which in turn are waiting for other resources to become available. So bringing that concept back to life, which is again the focus of any discussion that you have with me, the cyber professor, we talk about a good example being a couple of resources on our computer system, and we can say resource one could be a file that we have saved on our computer. It could be a database record, it could be a Microsoft Excel document, it could be a Microsoft Word document that you may have saved on your computer. Look at that as the example of resource number one, okay? And then for resource number two, you can take a look at, for example, a printer, an input-output device that you may have connected to your computer either via wireless or via a wire connection to your desktop or your laptop. So it could be a printer. So resource one, a file, resource two is a printer, and deadlock happens when the file, the Excel file, let us say it is an Excel file that we are talking about in resource one, is assigned to process one, and process one could be just a sequence of steps that you are taking to make modifications on the Excel file. So process one is the editing capability that you are conducting on the Excel file. By that I mean changing some of the information that you have on the Excel file. So process one, the editing that you are conducting on that particular file, is the one that is referred to in this picture right here. So the Excel file is assigned to that particular process that is running on your computer, and that particular process is waiting for the printer, which is resource number two, to become available. However, the printer cannot become available to that print request that you're making because the printer is assigned to another process that you're conducting on that particular computer, and it could be a different activity that you're conducting on the computer, and that same activity is the one that is already waiting for the Excel file to become available, so it can make some changes to the same Excel file that you are trying to access with process number two. So you can see the circular reference that we mentioned under the 4 conditions for deadlock, the circular wait. So one resource is assigned to a process, and that same process is waiting for another resource, which is at the same time assigned to a second process that is again waiting for the resource number one that we mentioned at the beginning of the circular reference. So this creates a deadlock state, and these 4 conditions must occur in order for a deadlock to be considered a deadlock in your computer system. And then we talk about live lock, a lock system whereby 2 or more processes continually block the forward progress of the others without making any forward progress themselves. So you can see the 2 processes kind of doing something in the background. You can see perhaps a red light flashing on your computer system, telling you that the hard drive is doing something for you. You may be able to see kind of a progress bar on the screen saying that the process is moving along, but at the end of the day it's not completing. So that is a live lock, and you cannot get either one of the 2 processes to complete. Now, how do you handle those situations? So there are strategies for handling deadlocks, which is the new topic that we are introducing today in our discussion. So what are the strategies for handling deadlocks? The first one is prevention. Whenever you're writing the code as a programmer, you can create some specific code that will allow you to prevent any of the 4 conditions that must take place for a deadlock to occur to become reality, to become true. So you write code that prevents any of the 4 conditions to become true. Either mutual exclusion, no preemption, hold and wait, or circular wait, any of those four need to be stopped at any point in time by using code that you make part of the program or process that you are creating as a developer, as a software developer. So you need to write rules or code to prevent any of the four conditions to occur. That is prevention. So ahead of time, you think about preventing deadlocks and you take that action in order to prevent deadlocks from occurring within your application. Now, avoidance is the second concept or second strategy that we are going to discuss today. When any process is requesting a resource during runtime, so now we are moving a little bit further in the process. So prevention happens way before when the software developer is writing the code, right? Avoidance happens right before the execution of a process in memory. So during runtime, when the process is already loaded into memory and is about to run on your computer system, that is when you check, or the system checks, is the requested resource allocated to any other process. If we allocate the requested resource, will it lead to deadlock? So you are checking, you are forcing your computer system to check those two questions before actually executing the process that is already loaded into memory, which may trigger the deadlock. So you are avoiding the deadlock right before the process is about to be executed. So prevention is way before when you are creating the code, even before the process is fully created in code. Avoidance is when it is already loaded into memory, the process is about to be executed. However, you stop it because you are making sure that you do these two questions. You check for these two questions to either be true or false, and then if you don't see any issues at that point, you allow for the process to run in memory. So that is avoidance. Then we move to detection and recovery, which in your textbook you may see as two different strategies. However, in my presentation, what I want to make sure that I do is I combine the two, because in my view that is the way that the operating system is handling the strategy to prevent deadlocks. So detection and recovery is together bundled into one. And the strategy is as follows. You first allow for the deadlock to occur. So you don't take any prevention actions when you're writing the code. You are not taking any actions when you are about to run the process in memory during the avoidance section. You let the deadlock to occur. So you let it happen and then detect it. And then the recovery process starts. So it's kind of, okay, you know that it's going to happen at some point in time, so why waste time preventing or avoiding it? Let it happen, and when it happens, we are going to deal with it. So that is the approach or the strategy of detection and recovery. And finally, we have the last strategy that I want to present to you, and perhaps it is not too clear or is not even presented in your textbook, but it's something that I want to contribute to you. Ignorance is the last strategy that we are going to talk about, and that is when no code or functionality is written to handle the deadlock. You may say, wait, what? You may say, why are you going to do that? Are you going to just ignore the fact that your computer can get deadlock at any point in time and not take any action? Well, to a certain degree, we can say that deadlock or deadlocks don't happen as often on a healthy hardware as you may think. So when it happens, yes, it is frustrating, it is painful because your computer is not responding, and perhaps you need to press the power button and hold it down for 5 seconds for the computer to be completely turned off, and then restart or boot up your computer again by pressing the power button again, and you may get an error message when you're booting up saying that your computer was turned off all of a sudden and you need to run some diagnosis or things like that. Yes, it is painful, it is frustrating, but does it happen every day? Does it happen every hour when you're working on a computer, on a healthy computer system? No, it doesn't happen that often. So ignorance is based on the fact that on a healthy hardware, you don't see deadlocks happening that often. So writing the code or functionality to prevent or avoid deadlocks is time consuming. It implies the use of human assistance in the form of programmers that are writing code, and it increases the complexity and reduces the speed of your computer system. So why spend all the effort, the resources to prevent or avoid deadlocks when they don't happen that often? So this strategy of ignorance is used in specific situations by Windows and Unix. So it is not crazy to go with that strategy to handle deadlocks. So that is another strategy that is available to operating systems to deal with the fact of life, which is deadlocks. Based on the frequency, which is not that high, we are going to take the approach of ignoring deadlocks and just moving forward. So that is the fourth strategy that is listed here. Now we move to the concept of starvation. And that is the result of the conservative allocation of resources, where a single job is prevented from completing its execution because it is waiting for resources that never become available. So that is a complementing concept that I want to put on the table for you, starvation. And there are expected and unexpected reasons for starvation. So we are going to talk about process scheduling errors and mutual exclusion algorithms and some of the expected reasons why you may see starvation within a computer system. For the unexpected reasons, resource leaks, and that may be part of some flaws that you may find in either the hardware or the software components. So there are instances in which the code that programmers write can create resource leaks within the application that they are deploying. And of course it is unexpected because the developers are not planning to write code that is going to promote resource leaks, because they will become really bad software developers, right? So it is unexpected and sometimes it happens. So it could be also a failure of the hardware itself. Denial of service attacks, and that is another unexpected reason why, because developers or the administrators of operating systems are not going to plan a denial of service attack on any of their computer systems knowingly and really wanting to do it. It happens unexpected because they are subject of cyber attacks or cybersecurity attacks, and those denial of service attacks create the instance of starvation within a computer system because of the nature of the cybersecurity attack, which is targeting the denial of services on that particular computer system and making it starve for resources. Then we move along to chapter 6. So the last slide that we discussed was the last component of chapter 5. Now we are moving to chapter 6, and we have 3 components that I want to make sure that we discuss. And specifically the first 2 are the ones that are really important for our discussion. So concurrency versus parallelism is the first objective that I want to accomplish during chapter 6, and then we move to typical multi-processing configurations, and finally the process synchronization software. So those are our high-level objective for chapter 6, which is going to be a quick chapter because we cover much of the concepts during chapters 4 and 5 that are also part of chapter 6. So on the surface, these 4 concepts concurrency being number 1, parallel execution being number 2, parallel concurrent execution being number 3, and parallelism being number 4. On the surface, these 4 concepts appear to refer to the same thing. However, they are different from each other. Now, if you talk to different people that are knowledgeable about operating systems, not everybody will agree or will have the full understanding of the 4 concepts that we are discussing here today. But again, I want to offer you the global view, the most complete view that we can come up with, so you are you have all the knowledge and you are equipped with all the knowledge that could be helpful to you when you decide to move into the workplace and you decide to do either networking, either cybersecurity, either software development, any of the areas of information technology that are critical to the operations of companies nowadays. You will be able to contribute a lot of knowledge to them by having a global view of all the different concepts that we are learning. Okay, so concurrency being the first concept that we want to clarify for you, it is when an application is making progress on more than one task seemingly at the same time to the human eye, and this is the important highlight for you, seemingly at the same time to the human eye. However, since the CPU can only do one task at the same time, what the CPU does is perform a task for a little bit, a tiny bit, almost invisible to the human eye, the time allocation, and then switches to another task for a little bit and repeats that back and forth switch several times until the tasks are completed. Okay, so to you, based on your human perception, you may believe the tasks are being completed at the same time. However, we know, because we are learning and we are understanding how CPUs work, they can only handle one task at a time, so they are not really handling 2 at the same exact time. What is happening is they are switching between task 1 and task 2 so quickly that you cannot notice the difference. Now, how can they switch back and forth, and why, and at what point in time do they switch from process 1 to process 2 or task 1 to task 2? They do it based on the algorithms that we discussed in the previous session, number 1, and thanks to the management of the operating system. And that is why we are taking this course, right? The operating systems course, because we want to understand how a computer is able to handle so many things at the same time. And it is thanks to the operating system, to your Windows operating system, to your Linux operating system, to your Android operating system, whatever operating system you're using. That is why it is so important to have an operating system that is robust, that can handle the switching back and forth between different tasks. Now, a depiction of the concurrency concept is listed here on this picture here that I am pointing at, with only one CPU being listed, and the fact that you have 2 different threads, and we already talked about threads, being handled by this CPU. And you can see thread number 2 is the one highlighted in light blue here. It is happening at any given time, and all of a sudden you see this line, this dotted line. This is a point in time in which thread number 2 stops, and it gives CPU allocation to thread number 1, which is depicted in purple right here. So thread number 1 is being handled by the CPU, and then all of a sudden this dotted line takes place. This is a point in time in which thread number 1 stops, getting the attention of the CPU, and it gives the attention to thread number 2. So CPU is taking thread number 2 at this point, conducting the activities in thread number 2, and at any point in time, this is the dotted line, it stops working on thread number 2 for a little bit, and it switches to thread number 1, and back and forth we go. So what is happening here to the human eye? You may say, oh, thread 1 and thread 2 are being handled by my computer at the same time. And imagine thread 1 could be opening a printer, opening a document on your computer, and thread number 2 could be sending a document to be printed by your printer that is connected to your computer. So the two things are happening at the same time to your human eye, but in reality the CPU is handling them one at a time. Okay, so it is two different operations that you're conducting on your computer. It could be browsing one page on the website under thread 1, and thread number 2 may be typing on a Microsoft Excel document at the same time while you have another window with the web browser and a website that you are browsing on your computer. So these two activities can take place because the CPU is switching back and forth between the two. Parallel execution. It is making progress on more than one task at the same exact time. This is possible on systems with more than one CPU, where each CPU is able to execute one task or thread at the same exact time. Another CPU is executing a different thread. So you have two CPUs, or it could be the same physical unit, the same CPU with two cores, and they are running two different threads, thread 1 and thread 2. And in this case, since this line is depicting the time allocation for each of the two CPUs, these two threads are happening at the same exact time. So you can see during the same time allocation, you see the two threads happening, the one in purple and the one in light blue. Why? Because you have two CPUs in your system, or two cores assigned to the same physical unit on your system, computing physical unit on your system, CPU, and they are actually happening at the same time. So this is the difference between parallel and concurrency. Concurrency is, to the human eye, you may think that they are happening at the same time, but no. Parallel execution, yes, indeed, they are happening at the same time, thanks to the availability of two CPUs on your computer system. Now, we move to parallel concurrent execution. So now we have two CPUs, similar to parallel execution, two CPUs, and it could be more than two. It could be 4, it could be 8. You come up with the numbers. So it could be more than two CPUs, but at least two. If you have at least two CPUs, then you may have parallel concurrent execution, making progress on more than one task, seemingly at the same time on more than one CPU. Okay? So you remember concurrency and the fact that to the human eye, these two threads may be occurring at the same time, but indeed they are not happening at the same time. Well, just multiply these by 2, because you have this CPU, the first one, doing the same thing, thread 1 and thread 2. These two threads may be happening to the human eye at the same time, but they are not. The CPU is switching between the two threads so quickly that they can be making progress almost at the same time. And then you have another CPU, a second CPU in your computer system that is doing exactly the same thing, but not with the same threads. It's doing it with two different threads, thread 3 and thread 4. And that's what you see here. So the two CPUs are making progress on 4 different threads. It could be more threads, but we are using just 2 for each CPU as the example, an easy example that you can visualize so you understand what the concept means. And finally, we have the last concept of parallelism, splitting a single task into subtasks which can be executed in parallel. So the dark green is one single task, one single process that may be being loaded into memory by your operating system, right? And that process, since it is significant in size, needs to be split in more than one part. Why? Because it will be handled quicker that way by your computer system and your operating system. again, the importance of the operating system that we are studying, is the one making the decision, hey, this task or this process is so huge, we better break it down in pieces so we can produce the output rather quickly for the user. So the operating system is always thinking about you and trying to give you the output as quickly as possible. So that is why this dark green process is being broken down for this example into 4 pieces. It could be more, of course, but to make it easy to understand and to make the concept come to life, we are breaking it down in 4. So that is why you see the red arrows pointing to the 4 light green rectangles that you see in this picture. So this large process is being broken down into 4 mini processes in light green, and they are being allocated to the 2 CPUs that are available in this picture, in this computer system. Now it could be more than 2 CPUs, of course, and then they become thread 1, thread 2, thread 3, and thread 4. And of course, we see that thread 2 and thread 3 are happening at the same exact time, and they are part of the large task that is depicted in dark green here. One of the threads, thread 2, is taking place on CPU, on the first CPU 1, let's say, and thread 3 is happening on the second CPU, let's say CPU number 2. And the same applies with thread 1 and thread 4. These 2 threads are happening at the same time on 2 different CPUs. And that is the concept of parallelism. So if you check out some of the different textbooks and the experts on operating systems, they will give you a clear difference between concurrency and parallelism. However, there will be some authors or people that are not really differentiating between the two. So with this explanation, you have a little bit more concept and a little bit more understanding of the differences, so you can have a good discussion whenever you are faced with these instances, either at the workplace or academic environment. So finally, next we are going to talk a little bit about typical multiprocessing configurations. So whenever you're dealing with more than one processor on your system, you may have different ways to configure the operations of those multiple processors that you have on any given computer system. The first one will be the master-slave configuration. Okay, so for master-slave configuration, you have a processor that becomes kind of the boss of everybody else. All the other CPUs are under the umbrella or under the orders of this master processor. That is the head. This is the boss of the CPUs. Okay, so this master processor is the one taking all the instructions from main system memory. Everything that is loaded into main system memory comes to the master processor first, and the master processor is the one assigned or given the responsibility of utilizing the slave processors that are depicted on each side of the master processor in this picture. And the master processor is the one giving jobs or assignments to the slave processors, and then the slave processors have the authority or have the ability to send back the output to the system memory. But they cannot get any instructions from the system memory directly. Everything has to go through the master processor. That is why a 2-directional or bidirectional arrow is here, but no bidirectional arrow is depicted here to the slaves. It is just a one-way communication. The slave CPUs can send output back to the memory, but they cannot receive instructions from the memory. New jobs from the memory are only handled by the master processor, which after that will assign the jobs to the slaves. And the master processor again is also the only one talking to the input-output devices, not the slaves processors. Okay, so these 3 right here are CPUs, 1, 2, 3. This is system memory, and these are the input-output devices connected to your computer system. Moving along to the loosely coupled configuration, that is the second multi-processing configuration that we are going to discuss. We have the same number of CPUs or processors. We have 3, processor 1, 2, and 3. However, they are equal. meaning they don't have any hierarchy between them. There is no boss that mandates what the other two will do. They are equally taking the responsibility of talking to the main memory, which is depicted here. They have their own main memory assignment, and they also have their own input-output device assignment. So the processor may be taking over, processor 1 may be taking over a specific thread or process that is loaded into memory, and then that process or thread is going to involve input-output devices, and this processor will be talking to the input-output devices related to that particular process or thread, and sending the information back to memory related to that particular thread that processor 1 is handling at any point given in time. The same applies to processor 2 and processor 3. They talk to each other to coordinate and make sure that they don't step on each other's toes, meaning if processor 1 is handling a specific process or thread that is given by the operating system, then it will send some information to processor 2 saying, hey, I got this thread, you don't have to worry about it, I got it. So processor 2 will not get in the middle and will take a different task, a different job, a different thread under its umbrella and work on that, rather than messing with the thread that was already assigned to processor 1. And the same applies to processor 3. Symmetric configuration happens when you have 3 different processors. In this example, it could be more than 3, it could be 4, it could be 8. So for this visual that we are utilizing to depict symmetric configuration, we are saying there are 3 processors. They are talking to main system memory, but they are not allocating a specific size of main system memory to coordinate their work. Main system memory is being depicted as one single block that is talking to 3 different processors. So some of the intelligence of the allocation of tasks, threads, and jobs is also handled at this level, the system memory level, and the input-output devices are also being shared rather than being separate or separately allocated to each of the processors. So that is the difference between symmetric and loosely coupled configuration. Finally, we are going to cover at a high level process synchronization software. So the success of any multiprocessing system, meaning there is more than one CPU running on that computer system, if it is multiprocessing, depends on the ability of the system to synchronize its processes with the system's other resources. So it is important to synchronize activities because they happen so quickly and there are so many at any point in time, and you need some type of rules and strategies to handle the synchronization. So mutual exclusion helps keep the processes with the allocated resources from becoming deadlocked and uses the following techniques. These are the techniques that you should know the name of, and perhaps a little bit of the definition for the exam. So for this, I need you to pay attention to your textbook and take a quick look about the definition for each 3. For the presentation, we are only going to name them. And the first one is test and set. The second one is wait and signal, and the last one is semaphores, PV, and mutex. So those are the techniques, the software techniques that we are going to enumerate here under process synchronization software. What I need you to do is just take a quick look at your textbook and understand the differences between the 3 before you take your quiz for this section of our content in the operating systems course. This has been a pleasure. This will, again, if we go back to the map, the course map, This presentation will conclude our discussions on number 2, processor management. So with this discussion, now we are ready to take the final quiz for section number 2 and move along to section number 3 next week, in which we are going to talk about another important aspect of operating system, which is memory management. So the same importance that we gave to processor management in the past 3 weeks, we are going to give it to memory management, and we are going to get onto the topics that are related to memory management. So we are closing the loop and getting closer to the discussions of the actual operating systems that are important to us: Windows, Unix, and Linux. The approach that we are taking, as we said, is covering the general concepts of processor management, memory management, system security management, device and file management, and networking concepts in general terms. And then we are going to apply these concepts to how Windows does every single thing that we have listed in the previous sections from 2 to 6. And then we are going to move to how Unix and Linux handle each of these activities in their own operating systems. And the same applies to Android. Okay, with that said, I thank you very much, and until next time.